what are we doing? What were we doing? What are we talking about? Yes. Anybody? Residues. Yes. Okay. We're using calculus of residues to solve, certain improper integrals, right? And does anyone remember what exactly we were doing at the end of class last time?
Simple poles.
Simple poles, right? So you have, right? So you have some function so you have some function on complex plane, and it has a bunch of singularities in the upper half plane, and those we were able to deal with. But what happens if there are singularities on the real axis? Right? And so what we finished up with was this lemma, right? That said the following lemma: if f has a simple pole T naught on the real axis, then what happens? Anyone remember? Okay, so you have your T naught here. Then the limit of the integral over C sub r of f, where C sub r is some curve of radius r, as r goes to 0, picks up what happens. It picks up half of what you normally get. So it picks up half of the residue at that point. Oh, I don't know. What am I going to do with you guys? Well, just hang in there and just watch. I guess what you can see is how classes run. Even if this doesn't make any sense to you, which it shouldn't. If it does, can I have your autograph? Yeah, so for future reference. But anyway, just watch, I guess. Just watch. Okay, so this was the result, right? That you pick up, right? If you went all the way around, you would get 2 pi I, right? It turns out if you go partway around, then you pick up basically some portion, some fraction of what you would pick up otherwise, right? Here we're going halfway around, we pick up half of what we would get, and we go all the way around. Okay, right? And so that was the result that we finished up with last time, and here's what we're going to use it for. So here's the proposition. F is suppose f is an analytic function in the closed upper half plane. With a finite number of singularities, z1 through zn in the interior, and some simple poles t1 through tl, simple poles on the real line. Okay. If there exists m, p, and r naught, where p is bigger than 1, such that f of z is less than or equal to z over z over p, for all for everybody outside of that radius in the upper half plane, then the principal value of the integral of f equals 2 pi I times the sum of the residue times the sum of the residues in the upper half plane plus pi I times the sum of the residues of the singularities on the real line. Okay. So did we say this last time? Did we put this up last time?
You stated it, but we didn't.
Okay, so we and I sort of sketched the proof, but we didn't. We were going to do an example of it, right? So, do people want to see the proof again, or are you? Is everyone okay with the proof, or do people want to see it again? Does anyone want to see it again? Close your eyes for a second. Those of you who are in the class, close your eyes for a second. Raise a finger if you want to see it again. Okay. Put your fingers down. Okay, open your eyes. We're not going to do it again. We're not going to do it again. It's a minority who wants to see it. Okay. Okay, great. Then I don't have to think about it. Okay. But let me sort of sketch out the picture, right? So, right. So you have this function. It's an analytic function. Those of you who haven't been here, analytic is sort of like a differentiable function. Okay. So you have something like an analytic function. It's on the closed upper half plane. It has a bunch of singularities. So there are a bunch of singularities here where the function blows up. Okay. These are the guys here, and then you also have singularities on. You also have some singularities. So these are the z's, z1 through zn, and then these are the t's, t1 through tl, right? And so, what's the idea? Can anyone tell me the idea? Yeah, Christian.
It's like before where you're taking the integral over the upper half plane, except now you jump over the ones on the axis.
Exactly. So you create this curve, you create this contour, right? You create this contour gamma, right, which goes up like this, comes down here, and then over each one of these guys, you take a tiny half circle. Right. And then basically, the statement that the integral over this thing, use the residue theorem to say that the integral over this thing gives you this, right? And then each of these guys gives you this thing, right? The integrals over these lines eventually give you the integral over the entire real line, and then there's one thing left over, right? The integral over this upper current. Now, what happens with that?
Vanishes.
That vanishes, right? Why does it vanish? Because of this, right? Because you have this condition that f of z is bounded by m to the m over z to the p, where p is bigger than 1, right? So that's what we saw before. Okay, and I should say that I don't remember if I said this last time, but similarly, if f is one of these e to the I z j z, right? One of these integrals, Fourier transform type integrals, with a greater than 0, and g of z satisfying Jordan's lemma, then the same result holds. Because if it satisfies the conditions of Jordan's lemma, then what you get is the integral over this arc is going to vanish again, right? And that's all you want. As long as the integral over that arc vanishes, then in the limit you're going to get this result. Okay. Anyone have any questions? Okay. So let's use it. We do some examples. So here's a simple example. The integral from 0 to infinity of sine x over x So, right. What are you going to do? You say, well, let f of x, f of z, be e to the iz over z. It has a simple pole at 0 with residue 1. Okay. So what does that tell you? You just use the theorem, right? And the theorem says that the principal value integral, right, of this guy, e to the iz over z, is going to be 2 pi I times the residues in the upper half plane, but there are no singularities in the upper half plane, so that's 0, right? Plus pi I times the residues on the line, right? So that's times 1, right? Okay. So what does that tell you? That tells you that principal value integral of sine x over x dx is just going to be pi. You take the imaginary parts of both sides. Take the imaginary parts of both sides, you get this. Right. And so, what does that say about this? Well, this is an even function, right? Sine x over x is an even function. And so the principal value integral converging means that each of these guys is going to converge, right? And they're going to give you half of that, right? So, so the integral from 0 to infinity of sine x over x actually exists, and it's pi over 2. Any questions? Another simple example.
Wait, actually, I have a question.
Yeah, great.
So, isn't it that if the principal value holds, not necessarily the whole negative infinity to positive infinity integral holds?
Yes, that's right. So the principal value integral holding, wait, what does that mean? That means that the limit from negative n and n goes to infinity of sine x over x dx exists, right? But this is an even function, right? So this is the same thing as saying that the integral of twice 0 to n exists, right? This is saying that this, and in particular this, limit exists, right? But and also the limit, also the left-hand limit going from 0 to negative n, from negative n to 0 also exists, right? So then what you get is that the integral from 0 to infinity and the integral from negative infinity to 0, both of these guys exist, and so the integral from negative infinity to positive infinity exists. Okay, so if you have a principal value integral for an even function, if the principal value actually gives you a number for an even function, then that actually does imply that your improper integral exists.
Okay.
So, but not in general. In general, if your principal value exists, you don't know if the improper integral actually exists.
Fair enough.
Other questions? Okay.
Wait, sorry.
Yes.
Isn't sine odd?
Yeah. So x and x is odd.
Okay. Okay.
So it's even. Okay. Very good. Okay. Okay, second example. Suppose somebody asks you to evaluate the principal value of something like this. X minus 1, x squared plus 4 dx. again, this is just a straightforward application, right? So you say, okay, I'm going to take my f to be e to the iz over z minus 1 z squared plus 4, right? Which has simple poles, which has simple poles at 1 and plus or minus 2i. Right, and that's basically it. You just apply the theorem. Right? The principal value of f right, from negative infinity to positive infinity, right, is going to be 2 pi I times the residue of f at 2i plus pi I times the residue of f at 1. Right? And then you just work out what those things are using your normal tricks, and you get some answer. So I'm not going to do it. It's peanuts. Okay, so we're going to, for the rest of the class, we're going to do a couple more tricks of calculation of residues, using the calculus of residues, and then we're going to finish up with sort of I don't know if it's an interesting application or not, but we're going to figure out, we're going to evaluate the sum of 1 over n squared from 1 to infinity. Who knows what the answer is? What's the answer? Pi squared over 6. Yeah. It's pi squared over 6. How do you know it? Like, what kind of method did you use to get it?
Fourier series?
Fourier series, yeah. So I think that's the better way to do it. But this is a complex analysis class. The Fourier series way would be a much better way to do it. But this is a complex analysis class, and so we're going to do it by complex analysis using the method of residues. Okay. So okay. So that's kind of cool. That's kind of cool. But again, the Fourier series way is much better. Okay. So more tricks of integration. So this trick is, I think it's called integration about a branch point. So just do an example. If you want to go, if you get sort of like exhausted by the like endless sort of meaningless things that I'm saying up here, you're welcome to go. That's fine.
Thank you so much.
Yeah, you're welcome. Don't feel bad. I understand that it could be sort of tiring. Okay, so here we go. Here's what we're interested in. Okay. So here's the integral we're interested in, and what we're going to do is choose the relevant you know, complex function. So choose f of z as log z over z squared plus 4 quantity squared. Okay. With the argument of z between negative pi over 2 and 3 pi over 2. Okay. So this is the the trouble. Those of you who are in this class know that there's trouble. This is a multiple value function, right? And so you need to fix a branch of it. So here's the branch that we're going to fix. The branch is, we're going to say that the argument lies between negative pi over 2 and 3 pi over 2. In other words, we're going to cut the complex plane along this ray here. Okay. So in other words, when we write log z, what we mean is natural log of the absolute value of z plus plus I theta, where, and let me write it like this: natural log of r plus I theta, where z equals e to the I, r e to the I theta, and theta lies between negative pi over 2 and 3 pi over 2. Okay. So take C sub r to be this contour. So here's our cut in the plane again. I'm going to go from call this r, call this r, this negative r. So I'm going up here, and you come back over here, and you avoid the origin, because that's where the cut is. Okay. Where we'll take the inner radius to be p, to be rho, and rho will be something smaller than 2. Why is it smaller than 2? Because we want to catch the residue of the we want to catch that singularity at 2i. Okay. So again, let's call this thing L1 and L2, and this upper guy, C will be the whole contour, and CR will be the upper part of the contour, and C rho will be this small circle here. Okay. So then, just as before, right? You have that the integral over the whole thing, right? The integral over all of C. That's to say, the integral of CR plus the integral over L1 plus the integral over L2 plus the integral over C rho, right, is this 2 pi I times the residue. 2 pi I times the residue of that 2i. Okay. Of course. Okay. So the integral over L1 plus L2 is 2 pi I times this residue minus the integral over CR minus the integral over C rho. Why didn't I write that the first time? Okay. So okay, so we need to calculate. We need to examine each of these things. We'll do this one first, and then this one, and then this one, and then this one. So calculating the residue. As usual, you take phi to be log z over z plus 2I quantity squared. Everyone okay with that? Right. Why do you do that? You want f of z to be phi of z over z minus 2I. Z minus 2I quantity squared. So that's what you do. And then what do we do? We want the residue at 2I. Well, what kind of a pole is it there? It's a double pole, right? So we what do?
Derivative.
Take the derivative, right? So we take the derivative of this thing and we evaluate it at 2I. You work it out, it turns out to be pi over 64 plus I times 1 minus the natural log of 2 over 32. So it's just an exercise in differentiation. Yeah, Christian.
Does 0 not count as a singular value of the integrand here?
It's not an isolated singularity. It's not an isolated singularity. Right? The function this
Oh, okay.
like this, it's not even a singularity. It's a branch point.
Because like you couldn't take log of 0,
Right.
so it seems like it's the same sort of behavior as taking 1 over or something.
Yeah, but no, it's not an isolated singularity. Your function is not analytic. Your function is not analytic around 0. Right? If you look away from 0, your function is not analytic there. It's not even continuous. You remember this? The log is multiple valued, right? So when you walk all the way around here, you come back and you're actually at a completely different value, right? You're at a different value, and so there's this discontinuity here, and so that's why we place this cut here, because if we make that cut, then your function is analytic outside of that cut.
Yeah.
Okay, and so that's the select. That's how one chooses the branch. Right? We've chosen a branch of the logarithm. Right? The logarithm is this multiple valued thing, and we're going to choose a particular branch of it. So it's analytic on the plane, excluding this cut.
Maybe you could have very well just done it the opposite direction, right? And chose the negative 2I? Or no, I guess that's not a singularity. But if there was a singularity on the negative
yes, absolutely.
plane,
Yeah,
and then you do the branching up vertically.
Could, yeah. So there's you could do it that way as well, but you're going to get the same answer. Yes, absolutely. Okay. So right now we figured out what this thing is. Okay. We figured out what this thing is, and the second thing we're going to do is show that we're going to get control of these guys here. So part 2 and 3, using crude bounds to control the integrals of the C rho and the integral of the CR.
Thank you.
Oh, you're welcome. Okay, so let's do C rho first. Okay. So what we're hoping will happen is that this is 0. Right? That's basically what you hope. that the integral over these curve guys is going to go to 0 as the curves get small and as the curve gets big. Okay. So we're just going to do this in a very primitive way. Say, okay, consider the integrand. Let's control the integrand. Okay. So we have this z squared plus 4 quantity squared on the bottom. What are we going to do with it? Right, the backwards triangle inequality. So what do I get down here? What am I going to get here?
Rho minus 4 squared. Or rho squared minus 4.
Rho squared minus 4 quantity squared, right? Which I'm going to write as 4 minus rho squared. Not that it makes any difference, but our rho is going to go to 0. Right, so just to make it sort of clean looking. Right, and then on the top, right, what do I have? Z is on C sub rho, so it's going to look like this, right? Rho e to the I theta, right? So this is going to be natural log of rho plus I theta, right? Where theta lies between negative pi over 2 and 3 pi over 2. Okay. Okay. We can assume that rho is less than 1, right? Because our rows are going to 0, right? And so we can bound this thing like this. And so what we get is negative natural log rho plus 3 pi over 2 over 4 minus rho squared squared. Everyone all right? Everyone all right that we should be all right? Any questions? Okay. Okay, so that's good, right? And so what does that give us? Right? So the absolute value of this guy is controlled by, well, the arc length pi rho, right, times this thing, negative natural log pi, natural log rho plus 3 pi over 2 over 4 minus rho squared squared. Okay, and you see what happens, right? As rho goes to 0, then as rho goes to 0, this also goes to 0. This vanishes via, you could use, say, L'Hopital's. You have this rho natural log rho term, and that will go to 0. Okay. right, this term on the bottom, you see is going to go to 16, right? The rho goes to 0, this goes to some constant, right? So you're going to have, you know, rho times some constant. Those will vanish. The only thing that you're worried about is the rho times the natural log of rho. But that will go to 0 by L'Hopital's rule. Okay. Now the second thing we're interested in is the limit as r goes to infinity of the same thing over C sub r. Okay, but basically the same argument yields this. Yields that the absolute value of the integral is bounded by pi r times the natural log of r plus some constant over r squared minus 4 quantity squared. Okay, right. And what happens to that as r goes to infinity? You can see it. Right? You've got r natural log r on the top, and you've got r to the fourth on the bottom. Right? R to the fourth beats r natural log r, and so that goes to 0. So putting what we have together, right? At this point we have that the integral, that if we let rho go to 0 and r go to infinity, then the integral of L1 plus the integral of L2 equals 2 pi I times the residue there, which is pi over 64 plus I 1 minus natural log over 2 over 32 plus 0. Right. Which is good. Okay. And now let's finish it up. So finishing it up. If we look at the integral over L1, that's right, this part we call it L1, from rho to r, from negative r to negative rho is what we call this is L1 and this is L2 and L1, right? So let's just evaluate those things, right? The first one, so let z be r e to the I times 0, where r ranges from 0 to r. So we make a parameterization. We make a parameterization of L1, and we get that this is the integral from rho to r of the natural log of r over r squared plus 4 squared. Plus I times 0. And then for the other guy, we'll do something a little bit funny. Let's parameterize negative L2. Okay, so we're going to do L2 in the opposite direction. And you'll see why in a second. It works out more nicely that way. So Z is then R e to the I pi. So R e to the I pi, that is negative R. Right? dz is negative dr. Right? And R goes from rho to R again. Okay, so that's a parameterization of negative L2. Right? And so we're going to get negative the integral over negative L2. Right? Negative the integral over negative L2. So when we write up the integral for negative L2, this will be natural log of R plus I pi over R squared e to the 2 pi I plus 4 quantity squared dr. Negative dr. Right. Which turns into the integral from rho to r of the natural log of r plus I pi over r squared plus 4 quantity squared dr. So don't worry if you feel lost. I think don't worry if you feel bored. I think even people who are in this class feel bored, feel a little bit bored. I don't know. I don't know. Okay, we're almost done. We're almost done. I don't know if you like it, but we're almost done. So putting it all together, right? The integral over L1 plus the integral over L2. Right? What does that turn out to be? I'm sorry, the limit as rho goes to 0 and r goes to infinity of the integral over L1 plus the integral over L2. What is that? That gives us the limit as rho goes to 0 and r goes to infinity of twice the integral from rho to r of the natural log of r over r squared plus 4 quantity squared dr, plus the integral from rho to r of I pi over r squared plus 4 quantity squared dr. Right? We just evaluated each of those pieces, and now we're just adding them together. Why are we doing that? Because that gives us the piece that we're actually interested in. Right? Remember what our goal was. Our goal was actually to evaluate this thing, right? Okay, and so here it shows up. And what we worked out before is that this thing is this, right? 2 pi I times pi over 64 plus I 1 minus natural log 2 over 32. Okay, and so what do? We see that the integral of interest is half of the real part of this right-hand side. The integral of interest, the integral from 0 to infinity of the natural log of r over r squared plus 4 quantity squared dr is actually half of the real part of this thing. So that's going to be pi over 32 times natural log of 2 minus 1. The end. Yeah, Christian.
I don't see how you got that. That's the. I don't see how you made that jump.
This is a real integral. This is an imaginary. This is, if you look at the left part, this is the real part, and this is the imaginary part.
Okay.
Right? So I'm just going to take the real part of the left-hand side. I get twice the integral of interest.
Oh, okay.
I take the real part of the right-hand side. So I take the real parts of both sides and divide by 2. Right? This thing vanishes, this thing vanishes. Right? And you end up with this, with 2 pi I times this divided by 2. Right? And at the same time, you also worked out another integral. Right? You could say we worked out what the sorry, that 2 applies to. Oh no, it doesn't. Sorry, it's just one thing. Right. The imaginary left-hand side equals the imaginary right-hand side as well. So okay. Okay. So the trick is actually not all that different from the trick you played before. Right? It's not all that different from the trick you played before. It's simply that, you know, we're taking this branch cut. We take this branch cut, and then we create the contour, and then we play exactly the same game as before. Right? So it's not that different. It's simply, you know, what do you do if your function has a multiple valued function in there? Right? So, and this is what you do. You take the branch cut, and then you integrate around it. Right? You take the appropriate branch cut. You wouldn't take, you know, some branch cut like this and say, oh yeah, I'm going to do that. Right? That's crazy. Okay, so you take a friendly branch cut, and then you create a contour that goes around it. Okay. Everyone all right? Yeah, Michael.
So if in this case, you're integrating from 0 to infinity. If you're integrating from negative infinity to infinity, would you even have to parameterize L1 and L2, or could you just determine your answer from that initial equation down below? When you down below on the right hand side of the board, you have the sum of those integrals equal to 2 pi I times, et cetera, et cetera.
So say one more time.
So if you're integrating from negative infinity to infinity,
yeah,
you're interested basically
of the real logarithm.
Yes. Would you just
Because the real logarithm isn't defined for the negative numbers.
oh, that's right. Okay.
Yeah.
Yeah. Sorry.
Okay. 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 The last trick. This trick will seem like something you would never think to do. When I was young, there was a cartoon book called "School is Hell" by Matt Groening, the guy who made The Simpsons. And so, before he made The Simpsons, he had these, Life is Hell cartoons, or School is Hell cartoons. And they were basically these sort of strange-looking bunnies, right? So it's basically like this. They're strange-looking bunnies, and they went through experiences, and some of them were more scary-looking than others. The scared guy was the main character, and I think it was Matt Groening himself, the scared bunny. Anyway, so there are all these books about School is Hell, and it said like the 9 types of professors. School is Hell, the 9 types of professors. And the one in the middle, I remember was called, it's like the genius from the other planet. And he says like, what I'm about to tell you is so impossible you will never believe it, but I tell you it's true. Well, that's what I'm going to show you. Yeah. So like the other ones were like the apparently friendly teacher, or somebody who tried to be your pal, but really was not your pal. Or like the goody, I forget, there's a bunch of them. Anyway. Yeah, this was on one of the office doors of one of the math professors at Princeton. Okay, so now we're going to do something that should be sort of shocking. It looks like we'll probably not get to the summation, but who knows, maybe we will. So here, we'll just do it as an example. 0 to infinity, x to the minus a over x plus 1 dx for some a between 0 and 1. Okay. So I guess it probably would have been helpful to you who are new, who are sitting in on the class. It so turned out that once the theory of complex analysis was established, then it was possible to use complex analysis to evaluate integrals that were completely unsolvable by normal methods. Okay, and so that's basically this whole section here. The method is called the calculus of residues. Roughly speaking, what goes on is that it turns out that in complex analysis, so here you're on the complex plane, it's not so hard to get the integral over this sort of closed curve. Okay, it's not so hard to get the integral over this sort of closed curve. Well, if you think about this integral over the closed curve, it comes in two parts, right? There's this integral which is on the real line, right? The real line sitting inside the complex plane, and then you have this integral up here, right? So you have this integral over the entire closed curve. That's to say the integral over part of the real line plus the integral over the upper half here, over this part, right? And it turns out that's easy to get. Easy to get once you establish a lot of theory. Okay. So then you say, okay, well that's great. That gives me one way of evaluating these real integrals, right? This gives us a way of evaluating real integrals, right? We take our real integral and we extend it. We add on to it this part here, and then it turns into an easy problem, an easy complex analysis problem, right? And that's basically what we're. These are all sort of methods of doing that, right? Here's our real integral, and then we're going to somehow use the methods of complex analysis together. Okay. I probably should have said that before everybody left. Okay, so so here's what we're going to do. Again, we'll take f of z to be z to the minus a. We have some complex variable function here. So recall that z to the minus a is e to the minus a log z. Now log z is multiple valued. Right? It's going to give you log of the modulus of z plus I times the argument of z. But we have to fix the branch of the log, right? So what branch? What branch should we use? In this case, we're going to do something called integration along the branch cut. Okay, so we'll choose the branch where the argument lies between 0 and 2 pi. So our cut in the plane this time is here. So we're going to cut there. That's actually the place that we're interested in integrating on. Okay, so now we're going to play our usual game. Let gamma sub rho r denote this path. So Again, here we have the singularity at -1. So here's the -1. We're going to choose rho. We're going to choose rho to be smaller than 1. Right? We're going to choose r to be bigger than 1. So radius rho, radius r. And what we're going to do is take two lines here. One is going to be u. So we go up like this, right? From here, we go to here. We call this lower guy L. It comes here, and we walk around the inside. As usual, we're going to call this the outside guy C sub r, the inside guy C sub rho. Right? We call this path L, and we call this path U. So at this point, pretend for a moment that it makes sense to take the argument z being 0 along u, and the argument being 2 pi along L. That's actually impossible, right, because we have our branch cut there. But in the end, what we're going to do is basically take a limiting argument. Okay, we're going to stop, just a tiny bit away from the branch, and then we're going to let it approach. We're going to take the limit as the branch gets as we get closer to the branch. Okay, on both sides, and that will justify this this make believe here. Okay. In that case, in that pretend world, the integral over u plus the integral over L plus the integral over C sub rho plus the integral over C sub r is going to be 2 pi I times the residue of f at -1. Okay. Yeah.
Is it not a problem now that it's on the real line? Because we had been taking integrals before where if there were poles on the real line, then what was it? Then we had to go around.
Yeah. So we're doing something completely different. Where in the end, when we do this limiting thing, we'll get the integral on the real line. We'll get twice the integral on the real line.
Mm-hmm.
Okay. So it won't be a problem. Yeah, it looks. That's why I said you're going to think that this is the wrong thing to do. Right? It looks like very much the wrong thing to do. You're right. You're right to feel this way. Okay, but in fact, it'll work out. Okay. So now let's just evaluate everything. Evaluating everything. First off, let's do the integral over L. Z to the minus A over Z plus 1 dz. Over U, excuse me. Okay. So that is right. E to the negative a natural log modulus of z plus I times 0 over z plus 1 dz, which is the integral from rho to r of e to the minus a natural log of r over r plus 1 dr, which we rewrite as r to the minus a over r plus 1 dr. The other one, the integral over L. What happens? Well, we're going to get e to the minus a natural log of modulus 2 pi over z plus 1 dz, which turns into the integral from r to rho, right, going in the opposite direction, e to the natural log of negative a natural log of r, e to the negative 2 pi I a over r plus 1 dr. Right? And so what we end up with is e to the negative 2 pi I a, negative e to the negative 2 pi I a from rho to r of e to the negative a ln r plus 1 dr. Right? Okay, so we get some constant times the integral times the integral we got before. Okay, so so if we add this guy together, you're going to get 1 minus e to the minus 2 pi I a times the something which in the limit would turn into the integral of interest. Right? That's good. Right? This is what we're interested in. Okay. So the other things we need to do are, you can guess, we're going to evaluate the residue, and we're going to show that these guys vanish. Okay. So So number 3, we need to get the residue. Let p of z be z to the minus n, where we take our cut as we have, right? Right. This is an analytic function excluding that cut, right? Z to the minus a over z plus 1 has a simple pole at negative 1. Right? So all we need to do is just evaluate this thing here. Right? So the residue is just b at minus 1, right? Which is, recall how you do this, right? E to the minus a natural log of 1 plus I plus I by pi. That's to say e to the negative a pi. Right. 5 minutes. 5 minutes. When we do it, we can probably do it. Okay, so number 4, crude control again. Okay, so we want the integral of 0 z to the minus a over z plus 1 dz. Okay, we want to show that. We want to show that this turns into 0. Okay. So right, so z lies on c sub rho. Z to the minus a, recall, is e to the minus a natural log modulus z plus I argument of z. So again, we're just going to use crude bounds and the triangle inequality. So if we look at if we look at this, right, we get that by normal. So let's assume that rho is smaller than 1. You bound the integrand in the obvious way, and so the integral is controlled by well, just 2 pi rho to the 1 minus a over 1 minus a. Which vanishes as rho goes to 0. Remember that a is between 0 and 1. Okay, almost done. Do the same thing. The limit looking at the limit of this thing, right? Same sort of argument. Right? The integral is controlled by 2 pi r to the 1 minus a over r minus 1. Right? R is bigger than 1 now. Right. So let me move the r to the a to the bottom. Right. So you've got 2 pi r on the top, and you've got this r, right? You've got r to the 1 on the top, and you've got r to the 1 plus a on the bottom. Right. And so, so this goes to 0 as r goes to infinity. Okay. So now we've got all the pieces. We're almost there. Right. So what do we get? Altogether, what we get is that the limit as rho goes to 0 and r goes to infinity of 1 minus e to the negative 2 pi I a r to the minus a r plus 1 dr equals 2 pi I e to the negative a pi I. Okay. Right. Because right, this is going to equal the residue plus the integral over those curves, but the integrals over those curves go to 0. Right? And so you see what happens, right? Our integral, the integral we want, okay. And so the principal value integral that we're interested in equals equals this 2 pi I e to the negative a pi I over 1 minus e to the negative 2 pi I. Okay. Which, if you do a bit of simplification, actually turns into pi over sine over a pi. If you use the definition of the sine. Okay. So it's easy, right? Okay. Okay. So okay, but the moral I think you want to take from this is that we actually didn't do anything We actually didn't do anything too fancy in these last examples. Right? I mean, there's this trick, and I've sort of there's that trick of approaching the branch cut from top and bottom. But other than that trick, this is just calculus. This is just using the residue theorem, right? So just use the residue theorem to evaluate these real improper integrals. Okay, that's it for today.